also interactive. There's a lot of things that I can share and talk about. I'm also involved in a number of companies, and some of the companies there is healthcare related, and one of them is Synergy, and I'll quickly refer to that. And we've got quite a bit of partners in the healthcare space, and the whole concept around big data analytics and healthcare and electronic health records are very topical and very relevant. And what we do is, and what I will do in this talk, just maybe to frame this very quickly, I'll spend most of the time on applications in biomedical engineering. That's almost like say the 60% of the talk. But I want to start off just with the framing things and talk about what I'm currently doing and what we're doing in the healthcare space. Then I'm not sure to what extent as people, do you have, who knows what machine learning is? Who's got to feel comfortable about machine learning AI? Just want to get a sense. Okay, so it's about 50%, or maybe less, 40%. So I do have an introduction. So I can actually, my whole career has been built in AI. I studied at Stellenbosch University. I've got actually a kind of a background thing here. And all I want to quickly say is what I'm interested in is to see how can we use smart technology to actually make a difference, make an impact. How can we shape a better future in the smart technology era? And we live in a world where you've got abundance of data, and I think especially in the healthcare space, there's so much opportunity to make a difference. So from a background perspective, I studied at Stellenbosch. I did my PhD in AI machine learning, computer science and electronic engineering. Then started a company called C-Sense, which was, I think, the first AI company that was sold to a multinational in 2011. For more than a decade, we just worked on the application of machine learning AI in multiple industries. Touch a little bit on healthcare, not a lot. It was more the industrial space, manufacturing space, and so forth, also financial services. But then sold the company to GE, and at GE I got in touch not only with GE Energy and power and transportation, but also with GE Healthcare. And it was fascinating to see what they're doing in that space and learned quite a bit in terms of that. And saw the opportunities around predictive maintenance, and obviously for GE it's around their equipment. Well, they've got expensive equipment and they want to do predictive maintenance around this. So there's another application around AI. If you look at their jet engines, there's about 2,000 sensors around that jet engine, and they would like to do predictive maintenance. They want to know exactly what's going on even while it's in flight. And the same with healthcare equipment as well. So fascinating, all those kind of applications. I then went into, I actually started, I wanted to actually pay back, and I wanted to say, how can we look at the ecosystem as well? How can we make a difference? And I started the Machine Intelligence Institute of Africa in 2015, and since then it's grown significantly, and I'll share a little bit about that. That is a vehicle that everyone here can use in the non-profit space, business space, and we've got PwC, Deloitte, we've got IBM and Microsoft, and all these kind of companies getting involved with sponsoring events. We are like a media partner for a lot of AI conferences as well. And what we are trying to do is to actually create this network of people that's interested in data science and AI and want to apply it to make a difference, and specifically here in Africa. So we don't want to be left behind, and we want to make sure that we can make an impact. So really that's where that fit in. The Juma thing was just also kind of an Africa thing, and there I was Vice President Data Science and Chief Data Officer, and the focus there, when we talk about big data analytics, there we looked at more kind of your basically the big data was the mobile network operator data, call direct records and stuff like that. So you're actually trying to look at affordability, credit risk, and so forth. But you learn a lot because there's millions and billions of transactions happening, and you need to analyze that. So you need to be able to work with big data and analyze data and unlock the value from that data as well. But then the rest of the stuff here is really focused on next generation AI. We live in a different world where I think I call it the API economy, where it's plug and play. With C-Sense, we've written everything in C++ from scratch, proprietary. Now it's a different world. It's plug and play, it's open source, it's TensorFlow, it's about PyTorch, all these frameworks are available, and you can, in a quicker fashion, solve problems as well. So I'll talk a little bit about that. But anyway, so this is give you just some sort of idea. Yeah, so I've mentioned my mission is around how can we use this technology, and so from a Cortex, maybe I just quickly on Cortex. So what we're doing in Cortex Logic is we're interested in solving the business problems, interested in solving end-to-end solutions. And to solve end-to-end solutions, you need to have your big data analytics infrastructure sorted out, especially if you solve those type of problems. So what we've done, we're looking at a joint venture also with Afrocentric, for instance, where we help them to monetize their data, and we're actually working directly with MedScheme. And we're looking at projects like hospital exception management, and there's so many applications where you can help them as well. But at the same time, we're also partnering, because what Cortex Logic is an AI engine for business and platform businesses. So when you've got lots of data and you've got your applications, you want to actually say, how do I actually create these end-to-end solutions? And it involves a lot of different things. You need to create the smart data layers, you need to create the data science, the algorithms, you need to actually automate that, and you want to integrate that into the business, create an end-to-end type of solution. So you need different types of people to actually address that. So what we do with Cortex Logic, and we work quite tightly also with the Machine Intelligence Institute of Africa, because we've got a lot of talent and people there as well. You bring them in and you help to create this end-to-end solutions, which is absolutely needed. Now, as part of this partnership, we're looking at even things like Artisan Biomed are looking at precision medicine and partnering with them to provide an AI engine for all the data that they generate. Mslanga Labs, for instance, at UCT, Musa Mslanga, gene expression, all that type of things. He wants to do all sorts of image analysis and stuff, and we can come in and help to create end-to-end solutions around those type of things as well. So very relevant. We've also partnered with a company called FEMI. FEMI is a big data warehouse that looks at privacy by design and also data governance. And as you know, with healthcare data, that's incredibly important. And to create that foundation around you need to look at proper foundation for healthcare data records that could be not only structured data but also unstructured data, obviously images and text and all sorts of different things. But you want to make sure that you've got the right meta layers on top of this to access this information in the right way and to have governance around that. So we're looking at potentially bringing this into other Afrocentric and potentially into we're working with the Medical Research Council as well. There's all sorts of discussions around that as well. And even Microsoft is involved and so forth. So there's some very exciting stuff happening, and we're trying to put it all together and to create these end-to-end solutions. But we can't do it on our own. So you need these other ecosystem players to help and put it all together. So for instance, GenBee is also, they digitize clinical data as well. So we're looking at working with them as well to see they've got a very important role to fulfill in terms of this. So you can see there's a bunch of players in this space. So, okay, so that was just a little background, and I can dig into that a lot, but what is really on this particular slide represented, this is what Cortex is doing. There's really three things. Enabling the smart data. And when I say just talk about smart data, it's really the big data analytics framework that allows you to deal with structured and unstructured data in a proper way, to deal with streaming data, to actually have it all sorted out. And the critical thing is to have rapid access to all data. And you can't automate. You can't automate any AI or have integrated real-time solutions, personalized on-demand solutions, if you don't have rapid access to all data in one place. So that is critical to sort that out. Then we're focusing on automated AI and then integrating that into the business. And it's really then, in general, if you look at other industries as well, we're looking at optimizing the business, creating a growing and satisfied customer base. There's a bunch of things, solutions, AI solutions around productive employees, and then the whole thing around IoT and smart systems. So we're looking at end-to-end solutions around that as well. Okay, so I'm not going to delve into that more. So this is just MIA that I referred to. So the focus is really on transforming Africa through AI, machine intelligence. And there's a list of partners. There's also tomorrow an event that MIA is also a sponsor and Cortex Logic is also a sponsor. It's called Deep Learning in Daba X. So you can go to the right website, even go to the MIA website and go to events, and from there you can go to see exactly what's happening. There's a range of very exciting stuff happening. I would say the last 2 years, say since 2017, the field has been exploding, and it's incredibly exciting. The people that you meet that want to help solve and make a difference. This is just showing the growth path. Okay, so I'm going to this is just a quick intro to AI and what's happening. I don't know if you've seen this slide before, but there's so many different, when you talk about the smart technology era, it's not just AI. There's blockchain, there is biotech, there's so many different types of things. But if you look at it from an AI perspective, it is kind of regarded as the fourth wave. And it's pretty exciting because it's all about how to unlock the value. And even with IoT and wearables, you create that infrastructure where you generate a lot more data to actually do something with. Now what's interesting is you get this exponential growth of data, and data utilization is going up. So obviously people are doing something with the data, but that gap is still increasing. The good news is that we've got a much richer toolbox, AI toolbox, that allows us to work with unstructured data, structured data, IoT, the wearable data, and to bring it all together to unlock the value. So there's so much opportunity to make a difference and unlock value. So all of these is just talking about that. So I'm going to skip a little bit about this. This is just talking about AI and what's narrow intelligence. All of these, we can go into all of this as well. So there was mention of deep learning. So I think what I would like to do is maybe just show one or two and then go straight to biomedical applications, which is very exciting. What all the potential is, what you can do with this. As some of you already know this very well, but machine learning is really just a branch of artificial intelligence that allows us to create systems that can learn from data effectively. And there's actually a kind of, if you look at some of the data, some of the techniques is more statistical based, not truly machine learning based. But for me, it's all part of that toolbox. And a very important addition to that toolbox is deep learning, which especially works so well on unstructured data, works with lots of different types of data, and put us in a position to apply AI on multiple levels. So you can apply AI just by unlocking insights from structured to unstructured data. But now also you can apply AI on the human-computer interface. So you see these kind of image recognition and text and natural language processing, all sorts of different things on that kind of level as well. So and with, say, intelligent virtual assistants, you can get sentiment analysis and all of that, and that feeds again back to the data lake. And you can improve your models again with that type of data as well. So it's actually also helping to produce more data effectively. And there's so many different layers of applications in that regard. And as we know, it's been driven by the big driving forces, the big data availability, the computational power, TPUs and GPUs, etc. That's all available. Okay, so just quickly in terms of machine learning, and I'm just going to cover a little bit of that, because in the biomedical application examples, we are going to talk about some of the supervised learning and unsupervised learning and even reinforcement learning. So there's different types of machine learning that's available. Most of the applications around supervised learning, and that obviously requires targets. You need to have labels, and in a lot of instances that is part of the problem because you need to generate that. But we can talk about that as well. But this is the typical the different types of machine learning techniques that you get. With machine learning, it's obviously all about prediction, and you can predict. There's so many different ways of predicting, because you can, for instance, if you want to predict a week ahead, 2 weeks ahead, then you can shift the data. You create different types of input-output modeling. So this is examples of what we know, and then we want to predict what we want to know, or what is the Monday stock price. You want to say what is Tuesday, that type of thing. very simple examples of that. Unsupervised learning is interesting. This obviously, there's a lot of research to improve this. We need a lot more algorithms in this regard. The brain is also working. There's a lot more unsupervised learning truly taking place. But the way we currently, the tools that we have in our toolbox right now is really focused around clustering. Then obviously you can get this dimensionality reduction type of techniques, which is also very useful and falls also in this category as well. And then I'm not going to bore you with that, but this kind of shows kind of a spectrum of techniques. And what you will find is we talk about shallow and deep. With deep learning, it's obviously you're adding more layers to it, and you will find these kind of techniques like convolutional neural nets and recurrent neural networks and so forth on this side. But you will find the traditional ones that also works well for certain applications, SVMs and random forest decision trees, boosting, all of those type of techniques. But then there's also probabilistic models, which it's got its place as well. So you need to know what techniques to use where. So let me skip some of that. But what this is also showing, and actually in tomorrow's talk, I'm going to deep dive into deep learning foundations, architectures, and applications, and actually going to cover a bunch of these architectures and algorithms that's available. But the incredible thing is there's so many tools available. It's now all about how do we use the right tools to solve the right problems. And what I will do in the rest of the talk is to actually just show a little bit more of that, what people are currently doing. Okay, so some of the things, I'm just going to show some examples here, but then we're going to go into the biomedical things. But this is, in terms of convolutional neural networks, for instance, what's really, this is just an example of how deep learning, how deep convolutional neural networks recognize a face, where it really creates this layers of abstraction where it first look at, say, edges, then goes to areas like nose or eyes, and then put it all together in faces and so forth. So you can, in a way, you can actually construct these kind of algorithms to actually do these kind of things. And we'll show you now where people get very innovative in terms of, say, drug discovery, where maybe it's not, the data that you use is slightly different, you need to prepare it. If you look at medical image analysis, obviously you can just work with those MRIs, CT scans, the data there as well. We're going to show some examples of that as well. But it's all about how to apply it. So let me skip some of these as well. What's also a very interesting type of model you get, and I actually did my PhD on recurrent neural nets, which is different to the other ones. We're looking at image analysis. So recurrent neural networks deal with time series data. So if you think about any time series data, audio or video or any of that, or language, this type of technique is very useful, and it's obviously being used in natural language processing and other types of things as well. But it can do things like, say for instance, based on this, you can say the clouds are in there, and then it will predict the word sky, for instance. Or if you give it context, I grew up in France, and then I speak fluent in French. And you can make those kind of predictions because it understands context. And with the latest versions of recurrent neural networks, like LSTMs and gated recurrent neural networks, you can actually go far back in time and keep that context. And it's also flexible enough that you can forget certain things. So for instance, you talk about someone, and now suddenly you talk about someone else. You want to lose that context and get into the new context. So you want that ability to switch on and off, and you want your neural networks to learn those type of things as well. So there are a lot smarter systems being built, and even neuron cells are being built to actually accommodate those type of things. So I'll skip that. This is just maybe some of the applications as well. So image classification, you can use it for image classification. You can use it for image captioning. So, and I've got some examples there where you can have convolutional neural networks that recognizes the images or things in the image, and then you can plug a recurrent neural network on top, and it will actually generate a description of what you've seen in the picture. And that is just, again, engineering, because it's using a combination of convolutional neural networks and recurrent neural networks. to actually do that. And if you look at even Alphago, I don't know if you heard about Alphago. Yep. So with reinforcement learning, it's a combination of deep reinforcement learning and Monte Carlo search. So there's an example of, here's our toolbox. Let's use these different relevant techniques, and we construct, engineer a solution to solve a particular problem. And in a lot of instances, you get super intelligence, or superhuman performance for that narrow application. Like Go, for instance, where the best players in the world are being beaten by Go, and it's not just search, it's actually based, it learns strategies and policies, what's working, what's not. And these examples, obviously, you can use it for driving cars and all sorts of different things as well. Sentiment analysis, so you can look at a sentence, a paragraph, and based on, with a recurrent neural network, you can detect what is the sentiment based on that. Or you can do many-to-many, that's translation. If you look at Google Translate, and Google is just incredible how good it becomes, and they all start pumping in a lot more sophisticated recurrent neural networks into that system. And you can also classify images frame by frame as well. Okay, yeah, reinforcement learning, here's the Alphago thing, discovering new knowledge. Okay, then you also even get generative adversarial neural networks where you can start off with, say, noise or, say, latent space, and then add noise, and you generate images, and basically what you're trying to do is to give this to a discriminator network, another network, again an example of where you use things in tandem or in combination of one another, and the one is trying to generate real images, and you feed it real images, and so it's basically, there's fake images that's trying to be real, and you've got real images, and you've got a discriminator network that's trying to figure out what is real, what's fake. And by giving that feedback, you're almost kind of giving labels back to that generator network, and in that way improving. Now it's trying to get better and better at generating images of what's real. Now, the reason, this is an interesting application. It sounds, okay, you can maybe use it for art, whatever, but when you look at biomedical applications, you can see you can actually use it in drug discovery. There's applications, if you apply, there's different areas of applications for this, which makes it very interesting. Okay, so I'm going to skip some of this, the third wave, and where things are going with AI. Okay, so I talked about deep learning. So just quickly, in terms of biomedical research, if you look at even funding and money being put in investment, and you look at all the industries, it looks like healthcare is emerging as the hottest area of investment. So that's the top one there. And it's going all the way to 2017 there. And you also see a bunch of new players entering the healthcare space. So we live in the smart technology era. You see a lot of disruptors. You see a lot of new platform businesses coming to the fore. And there's a lot of opportunity to actually make a difference and make an impact. There's some of these platform players as well geared to make a difference. But if they partner with the right companies, you can create incredible solutions. So this is just a list of, I will go through them in the other slides, but we can make the slides available as well. You can look at this afterwards. But this is just summarizing some of the applications. There's clearly computational pathology, tumor detection, segmentation that was discussed earlier, registration, touchless interaction in the operating room, navigation, image-guided surgeries, healthcare robotics, drug discovery, protein folding, etc. So if you look at medical image and diagnostics, what happens when the diagnosis is automated? So this is, it's obviously there to support the doctor, the medical doctor, but it says the algorithm will see you now. But this is really focused on diagnosis, and there's some examples that I will quickly show in terms of radiology, pathology, and dermatology, where this has been applied. We're deep learning, and some of the things that I've talked about has been applied. So here is an example of metastatic breast cancer where there's automatic detection of that. You start with there's obviously training and then testing. So in the training, to train these kind of models, you need lots of data. You can start with whole slide images, and you feed the training data there with normal and tumor or abnormal data. You feed that into a deep neural network, say a convolutional neural network, and then the end result is a probability of a tumor. And then when you take this model, obviously you can put new data, test data into it and do a classification. It will actually generate a tumor probability map where it will tell you what is the probability of a tumor in that particular area, for instance. Then if you look at dermatology, the same thing here. So again, an example of deep learning neural networks. You can see all the different layers there, using convolution, average pool, max pool, the whole thing there. But the end result is you start with a skin image, and then you've got, in this case, training classes up to 757. And then what they do here is a procedure to calculate the inference class probabilities from those training class probabilities. And then, in this case, they talk about 92% malignant lesions versus the benign one, which is 8%. So this is examples of, so it's all about getting access to the data and then having the right people to actually apply it in the proper way, generating these kind of things. So here's some other examples and some of the companies that's also in this healthcare space doing things here. So this is still just focusing on imaging. So obviously it's using convolutional neural nets. So where it's medical imaging plus advanced machine learning, and the first one is where they talk about prostate MRIs, and image is worth 1,000 blood tests. But Maxwell MRI is creating some very successful results there. And it's actually transforming the whole patient care experience. Artists talked about the first DA approval for clinical cloud-based deep learning in healthcare. Enlitic is another interesting company. Actually, one of the founders there was the guy that started Kaggle as well. He's Australian, but they're based in the US, and they are very focused on applying deep learning for a variety of things. In this case, also they can spot diseases early using chest X-rays. And then there's some other examples as well, with CT scans and so forth. Okay, I'll skip that. The last section here is just very quickly on drug discovery. And as we know, the cost of new drugs is pretty expensive. This is just a statistic, unbelievable actually, 2.6 billion, more than $2.6 billion growing. And the statistics around this, it takes about 10 years on average, only 12%, if you look at efficacy, the percentage of those being effective, and yeah, it costs about 2.6 billion. So this is just showing that whole phase that it goes through, and obviously drug discovery, preclinical, and this whole clinical trials, phase 1, 2, 3. And this is a statistic that just shows the big problem here is the efficacy, and it's really part of the cause of clinical failure in phase 2 and 3. And so efficacy is basically this here, and this big one in purple. Okay, so big breakthroughs happen when what is suddenly possible meets what is desperately needed. So we obviously clearly very expensive. We've got lots of data. We've got deep learning and all these kind of techniques, and we've got cloud computing, and we've got people that knows how to use these kind of things. So hopefully we can create those big breakthroughs. So basically what we're seeing now is the beginning of the AI revolution in pharma, and this is just some examples. You will see IBM Watson and a bunch of other examples here. Where things are really picking up, and it's really, well, here chemists pin hopes on deep learning for drug discovery, and they're exploring obviously these kind of things that we're using, evolutional neural net, current neural net, all these type of things for drug discovery. Now, so if you look at again, we're showing a little bit of neural network structure there, but the top end there, you can see the type of data that you feed into the system could consist of, say, chemical compounds that you represent, plus the activity data, and you feed this into a deep neural network, and then on the output you've got the prediction of drug activity on multiple targets. And it's like the multitask learning that's pretty much happening. You can tell where it's active, predict where it's active or inactive. So that's examples. And what you're trying to do is you want to use neural network for meaningful leads, and there's different types of techniques to discover things as well. So for deep learning discovery, so here is an example again using compounds, and basically this is very interesting the way they're using this. So again, people are getting very creative
around using these type of things. So you can see they're feeding in the compounds. The labels is obviously there for the prediction purposes. At the structure, you need to obviously turn that into, I think I've got a slide showing the encoding of structure as features. So there's the structure, the molecules, the features. So, and here is the table of the different types of features, and then you can obviously map that to properties. So again, some data pre-processing that needs to happen. So you feed that in there, and you can then generate, you can look at similarity and so forth. But here you can see a new compound that you've got a system that looks at that, but then you can actually utilize the information that you've got here. Obviously, you train the system, you train a neural network with capturing information in the weights of the neural network, and when you apply it, you can utilize that, and you can push data through it to actually get predictions, find out similarities, or where does it, will it work, what will it not work. So let me just, data repositories. And here's my last example here. So this is an example of, I talked about adversarial neural nets. Here's an example of adversarial autoencoder for new molecule development. And what was interesting by autoencoder, you use inputs, and you use the same inputs as the outputs. And basically what you're trying to do is to encode it. And you create kind of this middle layers, or this layer right in the middle, a latent layer, effectively, that's kind of description of the core characteristics of what you see in the input data. And the input data could be the fingerprint and drug concentration that you feed into. You'll see that on the input layer, but you'll also see that in the output layer. And what you do with this, the beauty of this is you actually have inputs, and the problem is always with supervised learning to have outputs or targets. So in this case, you have got your targets, and you train this whole system to have a proper latent layer that will actually produce the original output of the original input again. So you get a latent layer that's really key, and that you can work with, and you can do things with that. And then you can use this for toxicity prediction, and this is reverse informatics. This is truly the last slide, but where they've built a preliminary model for ADMET prediction. ADMET is absorption, distribution, metabolism, excretion, toxicity. And they talk about over 155 records across 36 different ADMET properties to facilitate 10-fold cross-validation to confirm scalability. And the results look pretty promising. So obviously we don't see the exact prediction there, but they say their analysis yielded 27 descriptors that helps to predict. And this subset is then fed into each of the 10 algorithms for model predicting and so forth. But anyway, so here are examples again where people are trying to be creative around how to structure the data, how to feed it in, how to use these kind of algorithms to actually get better predictions. And I think we're just at the start of where this will go. So very exciting times, and I think I'll conclude on that note. Sorry. So I know it's a bit late. Okay.